Okay, so this is part 2 of 2 videos covering replacement reactions. We just finished single replacement, so if you are just joining us, go ahead and watch that one first. And then now we'll continue with double replacement. So our double replacement reaction, if we were just review the pattern for double replacement, we have 2 compounds that swap partners. So if our first compound, let's say generic AB and CD, and then we swap partners, then we'll have AD and CB. So just like we had with the single replacement, our metals will swap with our metals, and nonmetals will swap with nonmetals. You only need to make one swap. So you should have 2 new compounds at the end, and always make sure that you have a cation and an anion in each of the compounds because they are ionic compounds. So if you end up having 2 metals, which would be cations, in one compound, you've done something wrong. And same if you have 2 nonmetals, which would be anions, in the same compound, you've made the wrong switch. So then you'll just need to make a different switch to make sure that you have 2 new ionic compounds. When we work with double replacement reactions, we will not use the activity series because they're both in compounds already. Instead, we will use the solubility rules. And the usefulness of the solubility rules is to tell us if a precipitate formed. And if you remember, a precipitate is a solid product. And generally when a precipitate forms, it will change the color of the solution. And all of our double replacement reactions are going to start out dissolved in water. So our reactants will always be soluble compounds, and then they will produce, hopefully the goal is to produce at least one solid. If we don't produce a solid, then no reaction happens because they're just a bunch of dissolved compounds, both at the beginning and the end. So what we're really looking for is for something in the products to produce a solid. So we'll use the solubility rules to determine the state of matter. So what we'll have to do to figure out if a reaction happens is determine the state of matter for each of the products because our reactants are automatically going to be dissolved. And the way we do that is through the solubility rules. And our solubility rules table are down here with example 2. We will talk about how to use this here in a moment. But the idea for our solubility rules is to determine if it's solid, which would be insoluble. Think like a rock. It is not soluble in water. So if I put a rock in water, it's just going to stay a rock in its solid form. It's not going to dissolve. Whereas a salt that is soluble, like table salt, if you put that in water, it will dissolve. It will look like a clear liquid. That would be soluble, and it would be described in our reaction as aqueous. If it's insoluble, it will be described in our reaction as solid. So in order for a reaction to happen, at least one product must be insoluble, which is going to be a solid in our reactants, our products, and that tells us that if all the products are soluble, or AQ, then no reaction occurs. And that's how we have no reaction for a double replacement. So yes, you will have to do all of the work every time for a double replacement reaction in order to figure out if it's soluble or not. But again, the purpose of double replacement predictions is to figure out what products we're going to make. So it can be beneficial to know if no reaction will happen. Maybe we're trying to avoid making a product that is unsafe, or we want to make certain products and know if it will happen. So no reaction doesn't mean that it's a bad answer. It just is a different answer than this reaction will happen. One quick note, I mentioned it earlier, we need to double check that all ionic compounds have a cation and an anion in our products. never to have 2 metals or 2 nonmetals. That would be something you made a mistake with, so you'll need to fix that. And always consider the ion charges and apply the Criss-Cross method for that compound. Don't just drag over whatever subscripts were on the reactant side. Use the Criss-Cross method appropriately, and then you will have new compounds. And it will be unbalanced, so then you would put coefficients in. Most of the time, I should say, it will be unbalanced because of different subscripts. And then you would balance using coefficients like we did last week. Today's activities, for our examples, we're just following the patterns. So then in the actual practice, it does tell you to balance. So only in our examples here, we're not balancing. After we do the examples, when you do your choose 8 that will also apply for our double replacements. Just choose 8 of the problems. So you're going to be doing half of them. If you want to do all of the problems, that will be extra credit. Okay, so now we have our examples. Let's do these together. First, let's take a look at the solubility rules chart and just talk about how to read it. So the first column says cation, and the second column says anion. And if you remember, every single compound has a cation and an anion. So if you have a particular pairing, then you can determine if it's soluble or insoluble. So for example, this first row of the cations, it says alkali metals, and that's the first group, the first column. They're all listed here on the periodic table. So if I had, let's say, potassium in my compound, and then any negative ion, literally anything it could be paired with for any of these. So if it's with carbonate, for example, my compound would be K2CO3. And look at that, it's in our first example. And see, it has AQ written after it. That's because soluble means it is aqueous in water. I know that's a little bit confusing. Students sometimes find that confusing, that soluble is AQ and insoluble is S. But such is life. So that's how we read our table. When it's split, for example, let's look at this one here. It has silver or mercury with the anion acetate. So let's say I had silver acetate. If that's the case, then I am reading this top line because my cation was up here. Then it would be insoluble. So this would be labeled as S. This guy would be. Okay. But any other positive ion, so literally anything on the periodic table, let's say magnesium acetate. That one, we're going to follow the bottom here, that's soluble. So we would write AQ next to this guy in a reaction for its state of matter. So that's just reading this table. For pairs, you'll just read it across the row, and if there's 2 that are split, the top one goes to the top option, and the bottom one goes to the bottom option. Okay? So let's go ahead and practice with some actual examples. We're going to determine the 2 new compounds by swapping, and then find their state of matter using the solubility rules. Then write no reaction if no reaction occurs. One quick note about the solubility rules chart here. This is simplified a little bit from, there's a couple of rules that are not listed on here that may not be perfect to true solubility. So if you're if you ever come across a compound that disagrees with this table, it is because this is slightly simplified. But for all of our purposes, this works perfectly, and we're going to use it because it's nice and organized and you don't have to memorize it. And I'm a fan of not memorizing things. Although I do know if you ever have a class in the future that needs you to memorize these, it's beneficial for you to be able to quickly determine if there's a reaction or not. So let's do our swap here. We have potassium, carbonate, barium, and chloride. What I like to do is just think about all of the ions that are present and just write them kind of as my work. So I have potassium, and I have carbonate, and I have barium, and I have chloride. And again, these charges, this is back from the ionic unit, so make sure you haven't forgotten these things. This is building on from last semester, so if you did not get that first semester, we might need to have some extra help sessions because this is very important and foundational for the rest of the semester. So for our new compounds, currently we have potassium and carbonate paired up. The only other option for a positive and negative is going to be potassium with chloride. And together, that looks like our Criss-Cross method will just give us KCl. Okay, and I'm going to leave parentheses so I can do the state of matter. I'm going to do that at the end, just so that I can keep one track of mind at a time. Right now we're doing the swap. Then our other pair is going to be barium and carbonate. Sometimes I see students accidentally write the anion first, but remember the cation always comes first in the chemical formula, and this is a +2 and a -2, which will end up being just 1 and 1 Ba CO3. Again, leave little parentheses for the state of matter. There's our new partners with the correct charges. Notice it's not balanced as written currently. So let's go ahead. Right now we're not worrying about balancing. We're going to look at the solubility rules. So our first one, we have potassium and we have chlorine. So there's actually two places where we could find the same answer, really. But I think the easiest one is going to be in this first row because we already talked about anything listed here in this first row paired with anything at all is going to be soluble. So that would be AQ. Now if we followed the other option, you'll notice that potassium is not listed in the top. It's listed in any other positive ions, so we would follow over to soluble and it would give us the same answer. So you have sometimes multiple options in the table, and whichever option you follow, it will give you the same solubility. Barium carbonate. Now I will generally look for the anion first just because that's where most of them are listed. But I don't see carbonate, so I'm going to look at barium and see if there's barium anywhere. I see barium here, but that's with sulfate, so that does not follow. And I don't see barium anywhere else, and I also don't see carbonate, so this would fall under my all other pairs, which is where I have simplified this chart slightly, because not all other pairs are insoluble that are on this list, but most are. So this would be insoluble, does not dissolve in water. There's our S. So now we have our equation, and we know that it does have a reaction because one of them is a solid. Okay, so there's our reaction for this double replacement with the correct states of matter. Let's go ahead and do the next one together as well. Okay, so we've got lead nitrate and hydrogen sulfate. And again, think about the ions and then make the swap. I'm going to write them here at the top and just kind of swap these out here. Okay, whoops. Okay, so we've got lead, nitrate, hydrogen, and sulfate. Now we'll make our new pairs. Lead is going to go with sulfate, and hydrogen with nitrate. Okay. Then we're just going to follow our chart here. I see sulfate, I see lead, so I'm going to follow this top line. Insoluble, there's my solid. And then I have nitrate with anything is soluble, so there's my aqueous. Better you get at following the table, the faster these will be. Go ahead and finish the other three, and then on page 5 and 6 and 7, pick 8 and balance those equations.